Thank you very much, Dr. Blish, for such fantastic presentation. Very interesting results. We will discuss some of the questions that were raised at the end, and we're now going to move on to the last speaker of this session. It's my pleasure to introduce Dr. Paul Klenerman, who is the Sidney Truelove Professor of Gastroenterology in the Newfield Department of Medicine at the University of Oxford. Professor Klenerman's group works on the immune response to infectious disease, focusing on both the host and the pathogens to unravel mechanisms of viral persistence and to define the key features of successful immune response against pathogens that can be harnessed to develop vaccines. Today, he will share with us some highlights of the work being done by the Oxford Combat Consortium. We look forward to your talk.
Thank you. So hopefully can everybody hear me? Yeah, thank you very much. I'm going to talk about this combat project, which we set up in April as the disease hit Oxford. And we focused on some of the same questions that the previous speakers have addressed. Oops. So yeah, the goal was really to understand the pathogenesis and some drivers and predictors of severe disease. Really, it's all focused on peripheral blood. We do have parallel data sets which we're trying to generate in lung, but these have come out much quicker. And I think we've been quite just in one of the questions that was just raised about the heterogeneity, and that's based on work that Julian Knight, who's underpinning a lot of this, has been doing in sepsis, and where he's identified essentially what he describes as endotypes or subphenotypes. And one of the distinguishing features of that approach is that we then have a series of controls that are based in sepsis, because the entire sort of framework for sampling was based on these sepsis programs in intensive care. And we also are lucky to collaborate with a group in London to generate some equivalently sick flu cases as controls. And we actually have a whole separate sequel study on those, looking at markers associated with death. It's a sort of a site-seek approach, just as Mars was saying, and we shared initially with those groups the protocol, so that we hopefully will be able to integrate all this data into some enormous combined data sets fairly soon. The patients are collected across these clinical phenotypes as probably very similar to what you really saw before with mild, severe, critical disease. There's a small longitudinal element, and there's some mild disease patients who are basically healthcare workers that we're picking up along the way. And then we have these sepsis groups, which are the SRS1 and SRS2 endotypes, are more or less pro-inflammatory phenotypes, who do or don't respond to steroids to different degrees. And the flu patients all had severe disease and were on mechanical ventilation, and some of them went on to ECMO as well. So it's a very sick group of flu patients to match with the critical COVID. So we got about 140 samples that we've kind of focused on, and we've got some additional ones to explore around it, but not so much for the site-seek. So this is the principle of the study. So we have got all these things running, and many of them complete. So we've got a set of data, just like Muzz, around the BCR, TCR, and site-seek, which incorporates the antibodies, of course, a proteomics and lipidomics set. We got some background serology with some autoantibodies, which obviously becoming increasingly interesting. We have looked for virus. I'm not going to talk about all of these at all, but I'm happy to answer some questions on all that. Fairly detailed clinical data sets, as you'd hope. And then we do have a set of specific assays for neutrophils and myeloid cells, which we tended to miss out because the groups are much more focused on T cells. So that's the principle. And then what we're trying to do is then generate all of these data sets. I'm not going to run through all of them. Well, we have actually generated almost all of them. And then the hard work, I think, becomes to integrate these. So we have tried to create a database which will be open with appropriate governance to the community, not just the UK kit, which Maz has already indicated, but hopefully globally. And the process we're going through is to try and integrate these different data sets, which is fascinating and challenging at the same time. So that's the current state of play. So I just describe some of the issues that we've been through and a little bit of the data, although, as I said, it's not entirely complete, but I'll just show you a tiny bit. So of course, if you start with the overarching data sets or cohorts rather, they're quite mismatched in terms of age, obviously, and also sex. So this is a bit of an issue. And then the sampling timeframe becomes equally an issue when we're trying to compare all these groups. So as you can see here, there's sort of big mismatches in some of these things across the groups. The London group is the flu, and we took a few additional samples from London for COVID just to check nothing much happened. Oxford and London aren't very far apart, but the processing might have been somewhat different. And as you can see, the categories fit exactly with what you would see in all the studies that have been published so far, according to the severity in terms of neutrophils. And as you can see in the sepsis group, you get an even greater rise in neutrophils, CRP, and D-dimer, which is a feature of this disease. But once we'd sort of spend a bit of time normalizing the group so that we'd selected the patients most appropriately, I think we ironed out a lot of those problems. So the age, although it's not perfect, is reasonably matched from healthy volunteers across to critical disease. And the sex differences have been, to some extent, minimized. The feature in the middle, I think, is just to describe that even within what we call severe disease, there's quite a lot of variation, and that morphs actually fairly seamlessly onto critical disease. And we've got these physiological parameters as well as these sort of categorical distinctions between the groups. So an enormous amount of effort has gone into that at the end, but I think it's a usual issue about clinical annotation being rather critical to kind of precede the deep immunology. So as far as the site seek goes, which I guess is the critical component for this discussion, we've, as I showed, done 140 patients using this approach. And this was slightly complicated in our case by biosafety concerns around the blood at the time, although we've subsequently shown that although you can PCR sequences from the blood of very severely ill patients for the first week or two, we've never been able to culture any virus, and that's available online, that publication, if anybody needs it to support their biosafety concerns. So we've, as is shown here, done that number of cells and roughly that number of clusters. As I said, the work's still in progress, but here's a kind of overall map of what we've seen. I think it would concur with what everybody else is finding, with broadly the same patterns of change and the same types of cells being identified. So that's just the overall map. And I'm just going to show you my favorite cells, just I can't resist it, so that you can pick out quite easily. I think they're in the sequel somewhere, I'm sure, because we found them also in a sequel data set, but they're clearly here on the site-seq, these mate cells, which are a decent proportion of your CD8s in humans. So they've got quite a distinct transcriptional profile or phenotypic profile, depending on what your approach is, with a combination of things like ROR-C, a very evident TCR TRAV chain, and just a set of chemokine receptors, which are very distinctive. So they're easy to pull out, and I think they're a very dynamic set in this disease, as they are in others, but because of the spectrum, you can see the changes. I'm not illustrating them here, but the changes in mate cell frequency and activation look to me at this point to be amongst the most dynamic in this hypothesis-free approach. So just another component to the study is this site-off. So we've done both conventional flow and site-off, and so this is just I won't dwell on it, but the kind of the panel. So of course it's all a predefined panel, and we've normalized some of the cell counts for this, and that's actually run quite smoothly in parallel using a cytodelics mix, which preserves the cells very simply at the point of care. And one of the points I just wanted to raise, which we're struggling with, it's a slightly philosophical one, is that we now have, as Maz has already shown you, really lovely data from CytSeq and broadly the antibodies, ADTs, and the single-cell RNA-seq annotations give you very similar readouts, but it's not absolutely one-to-one. And then when you add in the annotations from the site-off and any fax panels that you run, you do get these bits around the edge, which make some of the annotations for some of the smaller subsets, but not exclusively to those, a little more complex. So the truth is somewhere in between all of these, whatever that is. And I think we're just in the process of trying to find ways to merge all these data sets with confidence so that we know what we're actually describing. So then the final part is going to be to merge all these components together to create, again, hopefully very accessible outputs, which are an interpretation of the severity, the subphenotypes, and these biomarkers, so that we're preparing that for public consumption as we speak. So I should thank everybody. Like everybody who's speaking today, these are very big consortia to get together, and we've managed to get a real buy-in from people across the piece, from the clinical end right through to things people in maths and throughout the hospital, really. So anyway, many thanks to all of those people. And as I said, Julian Knight is really the driver of the single cell and has been instrumental in this. So thanks very much, and I'll join in with the questions.